Hello guys, welcome again to this video. And in this video, as I have said, we will try and do problems on methods of substitution, and we'll try to do as many problems as we can so that we understand method of substitution in a more clear way. But notice that this lecture obviously requires you to have a little bit expertise on differentiation, because as method of substitution is completely dependent on derivatives. Because every time you are going to substitute a variable for some other variable, what you're going to do is to find the derivatives of both the sides and use the differentiation. And you also need to realize what derivatives or what substitutions are we going to make, so that the integral may be reduced to a simpler one or a more elementary one. That is the entire goal. So let me give the heading. So method of substitution. Okay, so in this method, let us try and understand what to do by choosing some of the problems. Let us say we have a problem x plus 4 whole cube dx. Now this problem can be solved in multiple ways. The first way will obviously being you would try to evaluate this x plus 4 whole cube as a trinomial. Like what you can do is use the formula for a plus b whole cube and use it as x cubed plus 4 cubed plus 3 into 4 into x whole into 4 plus x, and what you would get is x cube plus 4 cube plus 12x into 4 plus x, right? So you can break it down as x cube plus 64 plus 48x plus 12x squared, and then you can integrate all of the terms separately, because all of them are just constant times some power of x, and we very well know that the integration of any power of x can be found out, because integration of x to the power n is simply x to the power n plus 1 by n plus 1 plus c, right? So obviously this is one method to do, but integration makes it a lot simpler for us, because when we use the method of substitution, what we try to do is we do like this. We substitute y equals to x plus 4. Okay, now when we do the derivative on both sides, what we get is we get dy equals to, now the derivative of this x plus 4 with respect to x would be equal to 1 plus 0, right? Because the derivative of x is 1 and the derivative of 4 is 0 dx. So what we do get is dy is equal to dx, right? So what we are trying to do is, when we are trying to convert the whole integration from a variable of x to a variable of choice y, we also need to find the dy in terms of dx. So the dy would be in some function of dx. Here it is equal, which is another case, which would simplify our integral like this: x plus 4 whole cube dx would just be equal to y cube dy, because you see we have substituted. Now it might seem a little bit dumb, because well you do see that we could have just simply found out x to the x cube dx, right? But it's not the case, as you will see. Now the integration of y cube dy is just y to the power 4 by 4 plus c, and this can be done because the variable of integration is dy here, right? And now after you've got the answer, you put back all the substitutions. So y was substituted as x plus 4, so what you do is x plus 4 whole cube by 4 plus c, which is the answer, right? So okay, so this makes x plus 4 whole cube by 4 plus c, and these are the two ways that we can evaluate this integral, right? Okay, so let us move on to another example, which would be a little bit more trickier, or maybe a bit tad harder than this one. Let us evaluate sine of ax plus b for real numbers a and b. Okay, for real numbers a and b. Okay, so how do we do that? Well, obviously in that case also, what we are trying to do is we are trying to substitute this thing ax plus b, because were it only sin x dx, it would have been easier, right? So let us name the integral as I, and let us substitute let us substitute y equals to ax plus b. Now, as in the previous problem, what we are going to do is we are trying to differentiate both sides to find an expression for dy in terms of dx, right? So, differentiating both sides, we get dy is equals to a into dx, because the constant b would disappear and a into x is into differentiation is just a, and we have an extra dx always, we, as I told you. So dy would be a dx, or in other words dx should be equal to dy by a. Okay, now this would turn our integration something like this. It would be sine of y, because ax plus b is y, and dx would be dy by a, and this would give you 1 by a sine y dy. Now we know the integration for sine y, it is just minus cos y, so the answer would be minus cos y by a plus c. And it's time to put back the variable which we substituted, which would give us cosine of ax plus b by a plus c, which is the answer for our integration. So as you see, like this kind of equations are this kind of integrals can be solved by using simple substitutions, but obviously there are harder ones. So let us try to find out another integral. Evaluate integral of 1 by 1 minus 2x dx. Now what does this resemble of? Firstly, because the simplest way we can evaluate an integral or to find out what to substitute is to find out the most recent or the closest integral which it resembles to. So as far as I can tell, this resembles to something like this, right, whose integral we known as ln of x. So if we can somehow transform it in this form, that 1 by some variable and d of that variable, we can do that. An obvious way to do this is to substitute 1 minus 2x, and since it is linear, we substitute y equals to 1 minus 2x. Now y equals to 1 minus 2x would give us a pretty easy way to evaluate this integral, because when you differentiate both sides, what you get is dy equals to minus 2 dx, right? And this would give you dx equals to minus dy by 2. Using this I should be equal to 1 by 1 minus 2x is just 1 by y, and dx is just minus dy by 2, right? And so the constant minus 1 by 2 comes out, and we have 1 by y dy. Now this would give us minus 1 by 2 ln of y plus c, and it's time to put back what we have substituted, which gives us minus 1 by 2 ln of 1 minus 2x plus c. So you understand that we are in every problem, what we are trying to do is we are trying to reduce the integral by using some magical substitution, or rather a rational one once you try to get the hang of it, to reduce it to an elementary integral we know of, and then evaluate it directly, and then put back the value of the variable once it is out of the integration to get back our result. So this is what we call the method of substitution. We'll see a lot more examples in the coming sections, obviously. So the general version for this one would be, the general version for this type of integral is dx by ax plus b, and you can evaluate it. So let us name it as I. Substitute y equals to ax plus b. Now when we substitute y equals to ax plus b, we can have dy equals to a into dx, right? Then I should be equal to integral of dx is dy by a, so put a 1 by a outside, dy here, and this should be y. So this would give you 1 by a ln of y plus c, and if you put back the value, it would give you 1 by a ln of ax plus b plus c, which is the answer. Okay. Now, next example what we can get is something like this. We can try and find out some of the basic theorems regarding this, like so this one is a tad harder, but what I'm going to teach you in regard to this problem would be something that you should remember in your way along. So this type of an integral is not something where you just magically find the substitution, but rather you literally look for something. So that something is determined by the following theorem. Theorem says that if you have f of gx into g prime x dx, this is the form of the integral, which as you can see is the chain rule. Then this is equal, then this is basically equal to the integral of f of gx d of gx, or you can say this is equal to f of y dy, where y equals to gx. So you just need to integrate the function f. If the function f is integrable to you in an elementary form, you would be done, right? Okay. So what we are trying to find is, if we can find some function which is a function of something, and the derivative of that function is already given along with dx, we can directly substitute that function. Why? We can see why. So given integral is I equals to 2x into root over of 1 plus x square dx, and we can substitute y equals to 1 plus x square. Why are we doing that? Because see, I realize that the integral of 2x into root over 1 plus x square can be solved if we were to eliminate this root over 1 plus x square thing. So when I substituted y equals to 1 plus x square, I saw that the derivative of 1 plus x square is just 2x, which is given along with dx. So 2x dx would be substituted into a single dy, which is what we wanted, which is basically the form of this function, right? So the derivative of 1 plus x square is already given outside. So when we do dy, what we get is 2x dx, and that is helpful because this turns into root over y into dy, where 1 plus x square got to y and 2x dx was written as dy. And this is an easy one because this is just y to the power half dy, and using the rule you can find it as y to the power half plus 1 divided by half plus 1 plus c, which is basically y to the power 3 by 2 into 2 by 3 plus c, which is the answer, right? So this is the integral and this is the answer, and we can just substitute back to get our answer in terms of x, obviously. So it is basically 2 into 1 plus x square to the power 3 by 2 whole by 3 plus c. This is our integral, right? So this type of integrals can be solved, but you need to be a bit cautious about them. So let us do another one. Evaluate dx. So we want to evaluate 4x by root over of 2x square plus 1 dx. Again, it should be noted that ddx of 2x square plus 1 is equals to ddx of 2x square plus ddx of 1, right? And ddx of 2x square is just 2 into 2x, and ddx of 1 is 0, which gives you 4x. So you see that 4x is already present. The derivative of the term of 2x square plus 1 is already present, And if that is so, what we can do is we can substitute y equals to 2x square plus 1, and thus we see that dy is equals to 4x dx, and this would turn our integral into something like this. But this just only means that it's y to the power minus half dy, and using the rule we can write it as minus half plus 1 by minus half plus 1 plus c, which is basically y to the power half, and this becomes 2 because it's a half in the denominator, and we can substitute back our answer to find it's just 2 into root over 2x square plus 1 plus c. If you differentiate this using the chain rule, you would find that the answer is basically 4x in divided by root over 2x square plus 1, which is amazing because differentiating something is very easy while integrating something is insanely hard, just because of the methods or the ways you have to look for, right? Okay, let's do another one. Evaluate sine of root x by root x dx. Now again in this one, as you can see, the only portion that is not going with the integral is the root x inside the sine, right? And we are kind of sure that whatever else is present in the integral should be the derivative of that, right? So let's see. We observe d dx of root x is just equal to d dx of x to the power 1 by 2. Now we have learned previously that the d dx of x to the power something is just the coefficient comes out, so the coefficient comes out, and the coefficient the power comes out as a coefficient, and the power is reduced by 1, which means it is half into x to the power minus half, or in other words 1 by 2 root x, right? So if we were to differentiate, what we would get is something like this. Let y equals to root x, then dy should be equals to dx by 2 root x, right? But we see dx by root x is also present, so what we get from this equation is dx by root x should be equals to 2 dy, and we can absolutely put this to get the integral as for I equals to sine of y, because root x is y, into 2 dy. Since 2 is a constant and is in multiplication with the rest of the integral, it comes out, and we only have to integrate sine y dy, which is just minus cos y, so it's minus 2 cos y plus c, and putting the value of y back, what we get is minus 2 cosine of root x plus c. This is the answer, right? So you see, like, this kind of integrals can be solved, but then again we have to be a bit cautious. So let us solve a lot more problems. Example 7. I will try to do this as much as I can so that you get the idea of method of substitution completely. And if you have any trouble in evaluating derivatives, please go back to the last videos to find out how to evaluate a certain derivative or how to do complex derivatives as well. Okay, so example 7, evaluate integral of 2x e to the power x square minus 5 dx. So let us denote the integral by I, so that I is equals to 2x into e to the power x square minus 5 dx. Note that now again in this integral we are trying to see that since the derivative of x square minus 5 is just 2x, what we can do is y equals to x square minus 5, which should give us dy is equals to 2x dx, right? Then on substituting, I is equal to e to the power y, and the 2x dx becomes dy, right? And you know the integration of e to the power y is just e to the power y plus c, and you put in the value which was x square minus 5 plus c. So this type of integrals, if you find the derivative of a term directly present inside the integral, try to substitute for that term so that you can reduce it into a common integral or an integral that you know of, okay? Because only then would it be easier for you to find out what to do. So we will continue our examples, but first let us learn one more thing. Let us do one more example, then from the next video we shall also do all the other indefinite integrals that we are required to do in the method of substitution, but also we will do some of the definite integrals, and we will learn how to do the definite integrals as well. So let us do this. This would be example 8, right? Yeah. So we'll continue from example 9 in the next video. So this would be the last example for this video. So let us do this problem where we have integral of cosine of x dx by 1 plus sine x. So this one looks a bit more tedious than before, but note that ddx of sine x is just cos x, right? So as we can see, cos x dx is present in the numerator and 1 plus sine x is in the denominator. So if derivative of sine x is cos x, then derivative of 1 plus sine x should also be cos x, right? So rather than going for the substitution y equals to sine x, what we can do is we can directly go for the substitution 1 plus sine x, then let y equals to 1 plus sine x, and from that we get dy is equals to cosine of x dx. This would give us our integral as y equals to integral of dy divided by y, which is just the integral. This integral is evaluated as a natural logarithm, right? So ln of y plus c, and remember the y is always positive, so it's rather a modulus. So the answer, by putting back the value of y, would be ln of 1 plus sine x plus c, which is the answer. So these are by far right now the easier parts of the integral, but we shall do some more integrals to find out how to do them, and then we shall move on to the next part where we learn how to do methods integration by substitution, and some other methods for evaluating indefinite integrals, such as, let's say, the surds and the radicals. And finally we can move on to definite integrals, which are of utmost importance, which is why you are learning indefinite integrals, right? Okay, so we shall meet in the next video. For now, please do practice whatever has been taught, because a lot of examples have been taught here, and for the related theory, please download the Breatter math app and watch the videos right in there, and also you can see the theory side by side. The link is in the description. Thank you.